So, Professor Jiang,
Just about.
Jiang, please. Yes,
Okay, thank you.
over to you. Thank you.
Okay, thank you very much. Good morning, everyone. It's really nervous to give a talk about. And the talk what I would like to talk is have two parts. The one part is the work by the DFH and the NSSC, which is before the satellite launch, and another part is the work I did with the DTU and the GLASS people, IWF and DFH after the launch and about the data processing. And the first, because the Kirk have told a lot about introduce the satellite, so I will just say something about our project is start at 2018, and maybe this the CNSA have agreed our project at the end of the 2020, and during the 3 years, finally our satellite finally launched at May the 21st this year at the Jiang Satellite Launch Center. And the next is some information about the satellite. The first, our satellite is flying between -41 to 41 degree latitude, and the altitude is about 50 kilometers to 500 kilometers, and nearly circular. And so, based on the calculation, after next October, the orbital is nearly a circle about 500 and 450 kilometers. And the mass is about 570 kilogram, and 10% is for the fuel. We aim to fly 10 years about this satellite, but after the few days ago, I just see the swarm flying until 2036. So I hope our satellite can live as long as that swarm. Okay, and our satellite is about 9 meters, and we have our AOCS don't have magnetic influence. And here is the payload, 8 payloads on our satellite. 8 payloads provided by 3 countries. The first we can see the A is the CDSM, which can provide the scalar magnetic data, which provided by Austria IWF. And thanks for winner here. And the B and C is the factor magnetometers, and the star track is provided by DTU. They are both on the optical bench, which provided by the BISSE Beijing, and the bone is also by the BISSE. And also we have another factor magnetometers provided by IGG China. But this magnetometer is not on the optical bench. Beside the payloads on the board, we also have the ESLR and the EPS on the satellite. They are provided by Shanghai at the Peking University. And DFH have some experience for to build a magnetic satellite. The Caesar is built by them, and based on this, now they have some improvement. The 3 things. One is the MMU for the DTU units, and one is the optical bench, and another one is for the bone. And another one is for the low angle driving. This is this things to how to say this is for the simple, just when the sun is on the left, our satellite flying towards the sun. When the sun at another hand, our satellite is, because our satellite is not flying like strangely. We have an angle between the angle. It's about we have 4 situations: 15 degrees, 25 degrees, and -15 and -25 degrees. So why we do that is because we want to we want a smaller magnetic influence, and the orbital bench can change can become smaller. And also we can have higher energy from the sun. This is how in fact for our we can see here how the first is about how to our low angle change, and the second one is the magnetic factor disturbing on the disturbing, and the third one is the higher energy output. And the next work is we calculated the Euler angle on the ground because no, which this work can provide the initial Euler angle for us here. And this is this there have a lot of change between this one from the FGM to the NEC part. And here they have something. The first is we choose the stable magnetic field, and the second one is the OB, and avoid the effect for the outside, and estimation the ground in fact, and using the better equipment. And here's the location for our test is in Jiang, Yunnan province in China. Is you can see the place is all surrounded by the mountains, and there is a lake in the middle. We just do the test near the lake, and here that because no people live in there, and so the magnetic is very stable there. And here the first one is when we doing this work, the temperature is 20 degrees to 25 degrees, and the humidity is 30% to 40%. And we have two protections for the star track here, inter and outer, to avoid the dice and the deviate. And the third is our yeah, we change how to say we change the angle for we change the angle for the alpha, gamma, and beta. Every time we change it, we collect the data for 30 seconds and do the calibrations. Here is our result in the Lijiang. We have 119 angles, and all these angles is independent. So the blue one is the factor is the data in VFM, and the red one is we change to the ASC here. And this is our result. We have 3 tests, and the residual is about about 2 to 3 net Teslas on 1 sigma, and the background magnetic field is 49,200 net Tesla, which means one net Tesla percent to 4.192 arc seconds, and the our residual is calculated by is about 1.2 arc seconds, which is familiar to the DTU give us. And the next one is the standable for during the launch phase. This which means our orbital bench is very orbital bench is very stable, and do not change too much for that. Also about our temperature, because in our satellite we have temperature control. I will introduce the temperature after the satellite launch, but this work is on the ground, and the temperature is only changed The angle between the VFM and the CHU is only changed 0.1 arcsecond because the temperature change, and it is the annual variation could be reduced to 0.42 arcsecond here. This is the result for that. The red one is the change. So if it is very smaller, and this is the bone is and I just introduced the bone is the bone is the 4.3 meters, and then the frequency is large than 3.2 hertz, and beyond the parameter the B1 and B2 is much larger than 1 to afford the heat-induced variation of the bone. And here's the way to the test for to calculate the inference between the different payloads and the inference from the satellite. We do this test in DFFH, and the result is the inference from the satellite, and the payloads between the payloads is less than 0.105 net Tesla, and this matrix is how we calculate the inference. This is the inference from the VFM to the satellite, the inference from the satellite at the CDSM locations, and this matrix is what I used to remove the inference for the infrared calibration. And this is the OB level. Their noise is lower than 0.1 PT at the 0.5 hertz, which is very and there's no observed difference in the at the 10 PT levels. So which is the inference from the OB is very smaller, which we don't ignore them. And this is the orbitals. As I said before, now our satellite is flying about 450 kilometers to 500 kilometers, and according to the calculations, next October our satellite will fly in about 450 kilometers like a circle orbitals. And here is our low angle changes. This is the infrared performance of our low angle changes. So from the June to August, our low angle change about seven times, and from 15 degrees to minus 15, minus 25, and back to 15, and changes. And because this change is now we don't this change is just the auto to do that. And also the molten will unload from the June 16th to the June 27th, there have 5 times unloading observed envelope about 2.7 days once, and every time we will cost the 6 gram fields, and it will cost the 7 seconds. And here is the temperature for the OB, and we can from the result we can see the temperature at the OB is very stable. So which the inference, maybe the inference from the temperature can we can reduce the inference. Also here is the temperature. Which is between from the May the 21st to August the 18th, and the temperature is do not change too much, about a few degrees. this is the DFH work. They minus the temperature from the Star Trek camera A and Star Trek camera B, and the temperature gradient is less than 0.1 degrees, and A and C, B and C is less than 0.6 degrees, and the variation is also just like they do the test on the ground is could be reduced to 0.242. And also the next is my work for the in-flight calibration and first modeling. This work will is thanks for the NSSC, DTU, IWF, and DFH. We do the in-flight calibration. I will introduce some result for the in-flight calibrations. And the first is our satellite orbitals. That's very interesting things. In the July, all night the local time for the local time, all night stat data is on the south, and the next month, the August, all the local time night side is on the north, which is about, according to the nearest calculations, is about 21 days or 26 days. I didn't remember that. And this is also the VFM temperature of the VFM. We can see that because the DFH control the temperature, so this change is very smaller. The EU is about 25 degrees to 29 degrees, and the CSC is -5 to 0 degree, and the CDC is from 0 to 3 degrees, which is very stable. And this is the infrared calibration. Sorry for the mistake. This is the infrared calibration for every days, which means I use the every day's data to do the calibrations. So we can see, ignore the testing. Every day the residual for the calibration is between 0.2 to 0.5 net Teslas when I do the infrared calibration. And this result I don't consider about the influence between the payloads and the influence from the satellite, which means if I minus this influence, maybe the result can be better. But also, of course, now the result is really good. And here is the infrared calibration when I use the all data from the August 17th to the until the October 4th. During this time, the CDSM have some tests, but for all this data, the residual is about the RMS between the factor data and the scalar data is about 0.432 net Tesla, which is also less than 0.5 net Tesla. And here is just I use the Macau satellite data compare with the Q7 models. We use Q7 models to calculate the Euler angles. The data we use is on July the 7th to July the 24th, and do the data selection about the KP, DSD, and the local times. And we can see the blue one is I didn't do the data selection, and the red one is I do the data selection, which means the quiet time for the magnetic field. And our residual is I think RMS is about 6.242 net Tesla. And here is also compared with the storm data. Because on the two poles the unmodeled external field is which make a large difference. But in the middle, the blue and the red one is the storm alpha and Bravo, and the Macau satellite is for the yellow, and which is very smaller and similar. This is and also I do the this work is I just doing the modeling only based on Macau satellite, and data residuals and okay, what's this? The RMC as here is 0.23 net when I only use the Macau satellite data do the modeling. And also here is the initial field Macau initial field model. When I combine the Macau satellite and swarm alpha, both the scalar data and the factor data. the model is internal field is 30 degrees and the circular variation is 14, and the external field is 2 degrees, and we can see the power is very close to Q's model, and the residual is is about 3.35 nanometer. It seems we can do better because the Chris just have down to the 1.9 nanometer, which very impressive. And here is my conclusion. Is now for now our infinite calibration is less than 0.5 nanometer. But we can do better. The result can be smaller. And the second one is the quantity of the Macau satellite data is at least as good as SWAM. Also, we have a very good consistent with the SWAM data. And also we have a lot of work to do. One is to remove the influence, improve the quantity of data and the model, and also do the calibration better. And here's my, thank you very much.